Beneath the surface of reality lies a silence so vast, so complete, that it cannot be touched by sight or sound. It is not the silence of empty space, nor the void between galaxies, but something deeper, a hidden field, an invisible ocean, that stretches across all of existence, every star that blazes in the sky, every atom that spins in the dark, every thought whispered in the corridors of the human mind. All of it rises and falls like ripples upon this unseen sea. The cosmos itself seems less like a collection of objects and more like a trembling surface of vibrations, endlessly weaving, endlessly becoming. Physicists give this realm many names: the vacuum, the quantum field, the wavefunction of reality. Yet behind the language lies a single haunting idea that what appears solid and real may only be the crest of a deeper tide, that beneath the visible lies a foundation where every possible outcome, every possible choice, every possible future already exists. Time, then, becomes less a river and more a map, not flowing forward, but already drawn, waiting for consciousness to trace its lines. A single particle may stretch across 1,000 possibilities, each one as real as the next, until the universe selects one path and discards the rest into silence, if such a field truly exists. If it holds every potential future inside its invisible currents, then fate, freedom, and the very nature of existence itself may not be what they seem. The question is no longer whether the field is real, but whether humanity is ready to face what it means. Is this the architecture of destiny itself, or the silent canvas upon which all futures are written? The search for the hidden field did not begin with questions about the future. It began with a simpler yearning, the desire to unify the forces of nature. At the dawn of the 20th century, physics stood on the edge of revelation. James Clerk Maxwell had shown decades earlier that light itself was not an isolated mystery, but the ripple of an electromagnetic field stretching invisibly through space. The field, once an abstraction, a mathematical trick, was revealed as real. It carried every spark, every beam of light, every whisper of radio. Suddenly, empty space was not empty at all. Albert Einstein carried the next torch. In 1915, with the general theory of relativity, he showed that space and time themselves formed a kind of field, a vast malleable fabric that bent and curved under the weight of mass and energy. Gravity was no longer a force pulling across distance, but a geometric warping of space-time itself. Stars, planets, galaxies, all moved like dancers upon a flexible stage. The concept of the field deepened. Reality was not built from isolated blocks, but from continuous structures that stretched across the cosmos. And yet, these triumphs left a fracture. The universe of the very large, explained by relativity, seemed utterly different from the universe of the very small, revealed by the growing science of quantum mechanics. In the subatomic world, electrons flickered between orbits. Particles behaved like waves, and probabilities ruled where certainty failed. It was here, in the strange mathematics of quantum theory, that a new vision began to take shape. In the 1920s and 1930s, pioneers like Paul Dirac, Erwin Schrödinger, and Werner Heisenberg wrestled with the question of what particles truly were. Were they points, indivisible grains of matter, or were they excitations of something deeper? The answer came with the birth of quantum field theory. This new framework suggested that every particle in the universe, every electron, every photon, every quark was not fundamental in itself, but a ripple in an underlying field. The electron was an excitation of the electron field. Light was an excitation of the electromagnetic field. Matter and force alike emerged not from isolated things, but from vibrations of invisible seas that filled all of space. The implications were staggering. Reality was not built from particles, but from fields. Particles were the fleeting disturbances, the crests of unseen oceans. Beneath them lay the permanent, eternal fields, hidden, yet everywhere. Still, the picture was incomplete. One puzzle in particular haunted the 20th century. If particles emerged from fields, why did they have mass at all? Why was the universe not a weightless, formless dance of light? In the 1960s, several physicists, Peter Higgs, Francois Inglet, Robert Brout, and others proposed a daring answer. Perhaps there was another field, invisible but universal, woven through all of space-time. A field that interacted with particles, slowing them, granting them inertia, giving them the property we call mass. Without it, there would be no stars, no planets, no life, only a universe of pure weightless radiation. This field, soon named the Higgs field, became one of the most audacious predictions in modern physics. For decades, it remained unconfirmed, a shadow in the mathematics of particle theory. Only in 2012, after years of searching at the Large Hadron Collider beneath the Franco-Swiss border, did the evidence emerge. A new particle appeared, fleeting, unstable, but unmistakable. The Higgs boson, the fingerprint of the Higgs field, was real. The discovery shook physics. The invisible had once again been revealed as the scaffolding of reality. Fields were not abstractions. They were the very fabric of the universe. But for many physicists, this triumph raised a deeper question. If unseen fields gave birth to the particles and forces we know, could there be others still undiscovered? Fields not yet measured, but perhaps more fundamental, perhaps even capable of shaping the entire destiny of the cosmos. The search expanded. Cosmologists began to wonder if the explosive birth of the universe, the mysterious acceleration of its expansion, and the strange quantum behavior of its smallest components might all point toward an ultimate, unifying field. A field not limited to defining what is, but also what could be. For in the mathematics of quantum mechanics, particles are never confined to a single fate. Instead, each exists as a superposition, a spread of possible outcomes, until the act of observation forces one path to be chosen. Beneath this bizarre behavior lies the wavefunction, a probability field that encodes all possible futures a particle might take. This probability field became the next great frontier of mystery. If every particle rests inside a haze of possibilities, then perhaps reality itself, the stars, the galaxies, the flow of time is also suspended in a field of futures, each awaiting collapse into the present moment, from Maxwell's rippling light fields to Einstein's bending space-time, to the shimmering quantum seas of QFT. Physics had uncovered layer upon layer of invisible structures, and yet, the more it revealed, the more it seemed there was still something missing, a field, deeper than the rest, a hidden architecture that did not merely shape the present, but contained within it every possible version of the universe. The idea was staggering, almost unbearable to contemplate. For if such a field exists, then the future is not written in front of us, it is already present, encoded in silence, waiting to be read. The revelations of the early 20th century left physics shimmering with possibility, but also with disquiet. The triumph of fields, of relativity, of quantum mechanics, each discovery carried with it a paradox. And at the center of these paradoxes stood a single, unsettling truth. The universe was not what it seemed. For thousands of years, human beings had trusted their senses. Reality appeared solid, definite, and dependable. Stones could be touched. Planets moved in precise orbits. Light traveled in straight beams. To believe otherwise was to question the very ground beneath one's feet. But in the quantum world, the ground itself dissolved. The discovery of the quantum wave function was the first fracture. In classical thought, a particle had a place, a path, and a momentum. It existed as one thing in one location. But in the strange mathematics of quantum mechanics, the particle was no longer a single point. It became a cloud of probabilities, a distribution of futures. An electron, unobserved, could be in many places at once. A photon could take every possible path between 2 points. The world of the very small was revealed not as definite, but as a shimmering haze of potentialities. It was this revelation that prompted Niels Bohr to declare that physics was no longer about what nature is, but only about what can be said about nature. The act of measurement, he argued, did not simply reveal reality, it helped create it. Albert Einstein recoiled at this conclusion. To him, the suggestion that reality flickered into existence only when observed was intolerable. He called it incomplete, a symptom of missing knowledge. God does not play dice with the universe, he famously insisted. But Bohr and his allies countered with experiments and mathematics that showed otherwise. The dice were real. Reality itself was probabilistic. This was the shock. The universe was not made of certainties, but of waves of possibility. What seemed like a solid particle was only the crest of a probability field collapsing into focus. And yet, the collapse was never explained. What causes the wave function, rich with possibilities, to shrink into the single outcome we perceive? Why do we see one reality when the mathematics suggests many could coexist? The question haunted generations of physicists. Some argued that collapse was merely an illusion, a shorthand for deeper dynamics still undiscovered. Others suggested that all outcomes exist simultaneously, branching into separate universes in an endless multiverse of diverging paths. Each interpretation carried consequences not just for physics, but for philosophy, for meaning, for the very concept of existence. Experiments soon deepened the strangeness. The double-slit experiment revealed that particles like electrons could behave as waves, producing interference patterns unless observed, in which case they behaved like particles again. Observation, it seemed, did not merely record reality, it transformed it. Then came the eerie phenomenon of quantum entanglement. Two particles, born together, could remain linked across vast distances, change the state of one, and the other responded instantly, as though distance meant nothing. 2. Einstein, this was spooky action at a distance, a violation of common sense. To others, it was proof that the field underlying reality was not local, not bounded by space or time. What emerged from these discoveries was a vision of the cosmos that defied human intuition. Reality was not a set of objects arranged in space, but a continuous interplay of fields, waves, and probabilities. Matter was not solid. Time was not fixed. Space was not passive. All were dynamic, woven from hidden frameworks whose rules often contradicted common sense. And within this framework lurked the most unsettling implication of all, that every possible future exists within the field until the moment of collapse. The world is not built from certainties, but from a scaffolding of unrealized possibilities. The stars in the night sky, the beating of a heart, the unfolding of history itself, all rise from a silent field where countless outcomes hover unchosen. Waiting, it was a vision that blurred the line between science and philosophy. For if every possible future exists in silence, then what does it mean to choose? What does it mean to live? The scientific shock was not merely intellectual, it was existential. Physics had torn open a doorway into a reality stranger than imagination. The universe, once thought to be a clockwork of precision and determinism, now appeared as a sea of probabilities, collapsing into the present with no explanation for why one path is chosen over another. Einstein and Bohr's arguments raged through the decades, but the mystery remained. The collapse of the wavefunction became one of the most enduring riddles in science. It was not just a technical problem. It was a revelation that the field beneath reality is not passive, not silent, but active, dictating the rules of time, causality, and existence itself. This was the shock. Reality, it seemed, was not the story we believed it to be. Beneath the surface of the world we know, another world stretched, a world where every possible future already exists, trembling, waiting to be chosen. The scientific shock of quantum possibility left physics standing at the edge of a vast abyss. If reality was built not from certainties but from probabilities, then the next step was clear: to look deeper, to measure further, to see whether the invisible fields of theory could be detected, mapped, and tested. The 20th century became an era of instruments, machines that extended the reach of human senses into the hidden domains of the cosmos. Particle colliders were built to smash matter into fragments, revealing the fields that hold it together. Telescopes were lifted to mountaintops and later into orbit, peering not only into distant galaxies, but into the first whispers of creation itself. Detectors were lowered into ice, into rock, into the quietest chambers on Earth, searching for signals too faint for the naked eye. From these instruments came revelations that deepened the mystery rather than dissolving it. Vacuum fluctuations, and the energy of nothing. Physicists turned their gaze toward the quantum vacuum, what was once thought of as empty space. But the emptiness refused to remain empty. Quantum theory predicted that even in a perfect vacuum, fields could never truly rest. They fluctuated ceaselessly, producing particles and antiparticles that flickered into existence only to annihilate a heartbeat later. These vacuum fluctuations meant that the void was alive with restless activity, a seething ocean of invisible ripples. Experiments confirmed this. The Casimir effect, observed in 1948, revealed that two uncharged metal plates, placed close together in a vacuum, experienced a subtle force drawing them inward. The cause was not classical attraction, but the energy of the vacuum itself. The pressure of quantum fields pushing from the outside. Nothingness, it turned out, was full of energy. The field was real, and if energy lay hidden in the vacuum, then the very fabric of the universe was far stranger than anyone had believed. Cosmic birth, inflation, and quantum fields. The telescopes then carried the question backward in time, to the beginning of the universe itself. In the faint glow of the cosmic microwave background, the afterglow of the Big Bang, scientists found patterns too subtle to ignore. Tiny fluctuations in temperature and density, fingerprints of quantum processes frozen into the fabric of the cosmos. The theory of cosmic inflation arose to explain them. In its vision, the newborn universe expanded faster than the speed of light in the first fractions of a second after the Big Bang. This expansion was driven, physicists argued, by a field, an inflationary field whose energy swelled space itself. Like an inflating balloon, the ripples in this field, stretched across the young universe, became the seeds of galaxies and stars. The great cosmic structures we see today, clusters of galaxies, webs of matter spanning billions of light years, all may have begun as quantum fluctuations in a field smaller than an atom. The implication was staggering. Not only did fields shape particles in laboratories, they shaped the birth of the cosmos. Reality itself may have emerged from a fluctuation in a hidden ocean of possibility. The holographic principle, information as field-but telescopes and theory soon hinted at something even stranger. Black holes, with their immense gravity, seemed capable of erasing information. Anything falling into them appeared lost forever. But the laws of quantum mechanics forbade such loss. The paradox led to the radical idea of the holographic principle. Perhaps the universe is not what it appears, not a three-dimensional structure, but a projection of information stored on a distant surface. If true, then the deepest field of all may not be energy, but information itself. Reality could be a grand encoding, each particle a pixel in a cosmic hologram, each possibility written in an invisible script on the horizon of space-time. Anomalies in the cosmic microwave backgrounds detectors grew more sensitive. Anomalies emerged in the relic light of the universe. Strange asymmetries, cold spots larger than predicted, alignments of cosmic structures that defied statistical expectation. Some physicists whispered that these might be hints, glimpses of structures beyond our observable universe, signatures of other fields brushing against our own, or scars left from a deeper architecture of reality, though unproven. These anomalies pressed the question forward. If our universe is a ripple in a field, might there be countless others, each with their own futures written in silence? The role of instruments. The deeper scientists looked, the more their instruments became like mirrors, reflecting not only the cosmos, but also the limits of human understanding. Particle colliders uncovered the Higgs boson, confirming the existence of fields that endow matter with mass. Satellite observatories mapped the microwave background with exquisite precision, revealing the fingerprints of inflationary fields. Neutrino detectors glimpsed particles that slip almost ghost-like through matter, suggesting hidden layers of physics still uncharted. Each discovery reinforced the same truth. The fields were real, and they held the keys to understanding reality. But with every key came a new locked door. The vacuum's energy was too great to fit into existing theory. Inflation's field remained hypothetical, never directly observed. The holographic principle stretched the very definition of space and time to breaking. The investigation did not dissolve the mystery, it deepened it. Toward the deeper field, what emerged from decades of measurement was a vision of reality in layers. At the surface, particles and matter, the tangible world of everyday life. Beneath it, quantum fields, oscillating seas that define the properties of particles. Beneath that still, vacuum fluctuations, inflationary fields, perhaps even informational. Structures shaping space-time itself. Each layer pointed downward, to something deeper, something unseen. And so the question sharpened, could there exist a field beneath all others? A universal field that does not simply define particles or forces, but encodes every possible configuration of the cosmos. A field that holds not only what is, but also what could be, every possible future, shimmering in silence. The deeper the instruments probed, the more this haunting possibility seemed less like philosophy and more like physics. The deeper physics probed into the hidden layers of reality, the more unsettling the vision became. Each discovery, from the restless energy of the vacuum to the echoes of inflation, hinted at deeper fields beneath. And with each hint came an escalation, a sense that the universe was not merely strange, but unstable, precarious, and far more mysterious than even the pioneers of quantum theory had dared to imagine. The rise of dark energy, the turn of the 21st century. Astronomers peered into the distances between galaxies, measuring how quickly the universe expanded. They expected to find that expansion slowing under the pull of gravity as matter tugged on matter across the cosmic web. Instead, they found the opposite. The expansion was accelerating. Some hidden agent was driving galaxies apart faster and faster, as though space itself were infused with a repulsive energy. The term dark energy was given, but the name only disguised ignorance. What was it? Some suspected it was the energy of the quantum vacuum itself, a latent pressure woven into space-time. Others argued it might be a new field unknown to physics, diffused across the cosmos and pushing it outward with invisible hands. The shock was profound. If dark energy continued, the universe's future was not a gentle slowing, but a ceaseless acceleration. A sky where galaxies vanish, one by one, beyond the cosmic horizon until only darkness remains. An invisible field, it seemed, was already writing the future of the cosmos. The fragile ground, false vacuum, decay, but darker possibilities lurked in the mathematics. If the Higgs field defined mass, and if the vacuum itself was not truly stable, then perhaps our universe was not resting in the lowest possible state of energy. Perhaps it was perched precariously in a false vacuum, a temporary plateau rather than a permanent foundation in this vision. A tiny quantum fluctuation could trigger a collapse, a bubble of true vacuum expanding at near the speed of light, rewriting the laws of physics as it swept through space. No warning, no resistance. A new universe born from the death of the old. The possibility, though remote, was not fantasy. Calculations of the Higgs boson's mass suggested that our vacuum might indeed be metastable. The ground beneath existence could be less solid than it appeared, a trembling field that one day might give way. Here was escalation, not just in mystery, but in terror. For the field that grants existence could also, in silence, erase it. Entanglement across the cosmos of vacuum, decay threatened from below. Quantum entanglement revealed a strangeness above comprehension. Entanglement showed that two particles could share a single state, no matter the distance between them. Separate them by light years, and still they behaved as one. To Einstein, this violated the very principle of locality, the idea that nothing can act faster than light. To others, it revealed something profound, that the field beneath reality is not confined by space or time. Entangled particles seemed to share futures. When one collapsed into a definite state, the other did too, instantly. The field was not a patchwork of isolated regions, but a continuous ocean where distance dissolved. Some physicists began to wonder if particles could be linked across galaxies. Could entire regions of space-time be bound together in hidden ways? Could futures themselves be entangled, destinies woven across the cosmos? The collapse of certainty, the cumulative weight of these discoveries pressed heavily on physics. Dark energy revealed a field driving the fate of the cosmos toward an unknown horizon. False vacuum decay whispered of a fragility at the root of existence. Entanglement shattered the boundaries of distance and locality. The deeper scientists looked, the less reality resembled a firm foundation, and the more it appeared to be a shimmering lattice of possibilities, fragile and strange. Gone was the vision of the universe as a solid machine, gears turning with predictable precision. In its place emerged a picture of cascading uncertainties, of hidden fields dictating not only the present, but the unfolding of all futures. The fear in the field, this was the escalation. The recognition that perhaps no solid ground existed at all. Each time physics dug deeper, what it found was not bedrock, but another layer of trembling possibility. Space-time curved and bent. Quantum fields flickered with uncertainty. Vacuum energy seethed in silence. Dark energy stretched the cosmos toward emptiness. What if physics was not moving toward a final foundation, but falling endlessly through layers of mystery? What if the deeper one searched, the more one found only further possibilities, never certainty? The human reflection, the implications extended far beyond science. If the universe itself is written on fragile, shifting fields, what does that mean for human existence? If every choice we make is only one collapse among countless unrealized futures, what does it mean to live a single life, to walk a single path here? The escalation of physics became a mirror for philosophy. The hidden fields did not merely challenge equations, they challenged meaning itself. And so, as the 21st century advanced, scientists found themselves not at the end of discovery, but in the heart of an ever-deepening mystery. The field that holds every possible future did not retreat under investigation. It grew darker, vaster, more terrifying, a universe accelerating into silence, a vacuum that may collapse, a reality stitched together by entanglement. This was not resolution. This was escalation. As the mysteries deepened, dark energy accelerating the cosmos, the possibility of a false vacuum beneath existence, the ghostly web of entanglement stretching across the stars. Science reached a crossroads. The old foundations of certainty had fractured. What remained was a universe that seemed to rest not on solidity, but on invisible frameworks. Physicists, confronted with this abyss, turned to theory. Not idle speculation, but mathematical visions, rigorous models built to wrestle with the unimaginable. Each theory was an attempt to glimpse the hidden field that might hold every possible future. Quantum fields. The universal sea at the heart of modern physics stands quantum field theory, the unifying framework for the particles and forces of nature. According to its vision, there are no isolated objects, no building blocks in the classical sense. Instead, there are fields, continuous and invisible, filling all of space-time. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. Even quarks and gluons are vibrations of their own underlying seas. The field is not passive. It dictates how particles are born, how they move, how they interact. Remove the fields, and the universe collapses into silence. In this framework, what we call reality is only the crest of a much deeper ocean, the shimmering tip of waves rolling through invisible waters. But quantum fields alone do not explain the full architecture. They describe the present, the particles we see, the forces we measure. They do not yet reveal the field that encodes every possible path reality could take. The Higgs field, the weaver of matter. Discovery of the Higgs boson in 2012 confirmed one such invisible framework. Without the Higgs field, particles would be weightless, slipping through the universe like ghosts. Stars would never form. planets would never coalesce. Life would never arise. The Higgs field is the silent sculptor of existence, endowing matter with mass, slowing particles into the dance that gives birth to structure. Its discovery was hailed as a triumph, a glimpse of the unseen. Yet its triumph also whispered of something more. If one invisible field could shape existence so profoundly, why not others? Might there be fields beyond Higgs, shaping not just mass but time, causality, even the branching of futures themselves? The quantum wave function, probability made real at the core of quantum mechanics, lies the wave function, a mathematical entity that encodes all possible states of a particle. A particle is not one thing, but many. Its wave function spreads across possibilities, here and there, fast and slow, alive with futures yet unrealized. Only when measured does one outcome crystallize. For some, the wave function is a tool, nothing more. For others, it is the most fundamental reality we know, a field of probabilities from which the present is drawn. If the wave function is real, then every particle in the universe exists in countless futures simultaneously. The collapse we observe is not the end of possibility, but merely the path we happen to follow. In this sense, the wave function could be the very field we seek, the field that holds every possible future, humming silently behind the veil of the present, the multiverse. Hypothesis. Every future realized, one of the boldest speculations arose from this logic. If every outcome exists in the wave function, perhaps collapse does not discard futures at all. Perhaps each possibility unfolds in its own universe. In this vision, the many worlds interpretation, the cosmos branches endlessly. Every decision, every quantum fluctuation, every particle measurement splits reality into parallel strands. Countless futures are not merely possible, they are real, each playing out in its own version of the universe. For some, this idea is extravagant, an excess of imagination. For others, it is the most straightforward reading of quantum theory, requiring no collapse at all, only the recognition that possibility is as real as actuality, if true. Then the field does not hold futures as potential, it holds them as fact, each realized in a branching multiverse without end. String theory and quantum gravity, the loom of space-time at the farthest edge of speculation lies string theory, an attempt to reconcile quantum mechanics with Einstein's relativity. In this vision, the particles we see are not points but vibrating strings, their harmonies producing the forces and masses of nature. These strings do not float in space, they weave space itself. Space-time becomes a product of vibration emerging from deeper patterns. Some versions of string theory propose extra dimensions beyond the familiar, curled tightly into scales too small to perceive. Here, the field is no longer just an ocean of probability. It is the loom upon which space-time itself is woven. To grasp the field is to grasp the architecture not just of matter, but of the stage on which existence unfolds. Cosmic inflation. The field that birthed the universe, cosmic inflation, added yet another layer to speculation. If the early universe expanded at unimaginable speed, it must have been driven by a field, the inflationary field. For a fleeting instant, this field dominated reality, swelling space-time in a violent expansion that smoothed the cosmos and planted the seeds of galaxies. Though the field itself has never been directly observed, its fingerprints linger in the cosmic microwave background, in the distribution of galaxies, in the very structure of the universe. Some theorists suggest that inflation may not have ended everywhere. In this vision, pockets of space continue to inflate, birthing endless bubble universes with different laws of physics. If true, our cosmos is only one future among countless others, each born from the fluctuations of a field that still trembles in silence. Information theory, the field of Codezemid. These vast theories came an even stranger possibility, that the fundamental field of the universe is not energy, but information. The holographic principle suggests that the universe can be described as data encoded on a distant surface, projected into the 3 dimensions we perceive. In this view, reality itself is a kind of computation, a field of information unfolding like code. Every particle, every force, every possibility could be a bit in a cosmic algorithm, a ripple in the field of information that holds not just one history, but all possible histories. The speculative horizon each of these theories, quantum fields, Higgs, wavefunctions, multiverses, strings, inflation, information, is incomplete. Each answers one part of the mystery while leaving deeper questions unresolved. But together they reveal something extraordinary, that beneath the surface of reality lies not emptiness, but structure, not chaos, but possibility, a field of hidden frameworks that dictate not only what is, but what can be. And in that recognition lies the most haunting speculation of all, that the universe is not simply a sequence of events unfolding, but a library of futures already written, waiting for the present to select its page. The field is the silent book of time, and we are its readers, turning pages without knowing how the story was first inscribed. Theories, however elegant, cannot stand alone. They must be tested against the universe itself, against the raw evidence written in starlight and particle collisions. To probe the hidden fields of reality, science has built its most ambitious instruments, machines that span continents, telescopes that peer back to the dawn of time, detectors buried in rock and ice, all in pursuit of whispers from the invisible. If the field that holds every possible future exists, it will not be found in metaphors. It will be glimpsed in data, in patterns that betray its presence. In the delicate tremors of space-time and matter, the Large Hadron Collider, probing the subatomic seas beneath the border of Switzerland and France. In a ring 27 kilometers wide, the Large Hadron Collider LHC hurls protons into head-on collisions at near the speed of light. When they collide, they shatter, releasing energies not seen since the first instance after the Big Bang. It was here, in 2012, that the Higgs boson emerged, confirming the existence of the Higgs field proof that invisible fields shape reality. But the search did not end with Higgs. Physicists continue to sift through the debris of collisions, searching for anomalies, deviations in particle behavior, hints of new forces, signs of fields beyond those already known. Dark matter, dark energy, supersymmetric particles, each could be evidence of deeper frameworks, hidden layers of the field. The LHC is not just a machine for smashing protons. It is a machine for tearing open the veil of possibility, for peering into the fields that govern all futures. The cosmic observatories, windows to the beginning, mountaintops, and in the void of space, telescopes stretched their gaze across billions of light years. They do more than collect light. They gather time itself. Photons that have traveled since the dawn of the cosmos. The James Webb Space Telescope peers into the faint red glow of the earliest galaxies, searching for the fingerprints of cosmic inflation, subtle patterns in how galaxies cluster, in how starlight bends under gravity, reveal the presence of dark matter and dark energy, invisible scaffolds that point toward hidden fields. Meanwhile, satellites, like the Planck Observatory, have mapped the cosmic microwave background with exquisite detail. In its faint ripples lie the frozen imprints of quantum fluctuations magnified by inflation. These patterns may be the clearest evidence yet that fields gave birth to structure. That probability shaped the very skeleton of the cosmos. Future missions, the Nancy Grace Roman Space Telescope, the Euclid spacecraft, aim to map dark energy's effects on the expansion of the universe to determine whether it is constant or evolving, whether it arises from vacuum energy or from a new field altogether. Each observation brings humanity closer to glimpsing the field that silently dictates cosmic destiny. Gravitational wave detectors, listening to the fabric of space-time in 2015. The Laser Interferometer Gravitational Wave Observatory LIGO captured the tremor of space-time itself, the collision of two black holes rippling across the cosmos. It was the first time humanity had heard the fabric of the universe vibrate. Gravitational waves are a new messenger, carrying information from realms invisible to light. They may one day reveal the imprint of inflationary fields, vibrations. From the very birth of space-time, future detectors, such as the space-based LISA Observatory, will search for these primordial echoes. If found, they would be direct evidence of fields that predate matter, fields that may encode the library of all futures. Quantum experiments, testing the collapse in laboratories. Physicists probe the foundations of quantum mechanics itself. Experiments in quantum computing manipulate entangled particles with exquisite precision, holding them in superposition across countless futures before collapse. Others attempt to test whether collapse is triggered by consciousness, by environment, or by some hidden mechanism yet unknown. Some theories suggest gravity itself may cause wave functions to collapse, linking the quantum and the cosmic in a single framework. Every experiment is a step toward answering the riddle: what chooses which future becomes the present? Is collapse an illusion, with all futures realized in a multiverse? Or is it a fundamental process, the universe narrowing its own possibilities moment by moment? The search for dark matter and dark energy around the world. Detectors buried deep underground or in frozen ice search for dark matter, the invisible mass that outweighs all visible stars. If discovered, dark matter could reveal a hidden field, a new framework beyond the standard model of physics. If dark energy's nature can be pinned down, it may expose the most profound field of all, a force shaping not only the fate of galaxies but the trajectory of time itself. Experiments like DESI, the Dark Energy Spectroscopic Instrument, and surveys like LSST at the Vera Rubin Observatory will map billions of galaxies, tracing the expansion of the universe across cosmic time. They may yet uncover whether dark energy is constant or whether it changes, a signal that a dynamic, evolving field is at work. The horizon of testing each tool, the collider, the telescope, the detector, the interferometer, is not an end but a question. Together they form a vast apparatus aimed at the invisible, straining to glimpse the architecture of the field. But with every measurement, new mysteries emerge. The Higgs boson's mass suggests a fragile vacuum. Dark energy resists explanation. Entanglement defies distance. Inflation's field remains unobserved. The instruments do not simplify. They deepen the enigma. It may be that the field which holds every possible future is not something that can be fully observed, only inferred. Its presence may be etched into patterns, anomalies, subtle deviations in data that point beyond the visible world. The human element there is something almost mythic in this pursuit. For thousands of years, humanity gazed at the night sky with the naked eye. Now it builds machines larger than cities, telescopes that see across cosmic time, detectors that listen to the tremble of space-time itself, all to glimpse what cannot be seen. The search for the field is not only a scientific endeavor, it is a reflection of human longing, the need to know whether reality is fixed or fluid, whether the future is open or already written, whether existence itself is chance or necessity. And so the quest continues. Each collider run, each telescope image, each particle detection is a message sent into silence, a question whispered to the field, and sometimes the silence answers. The instruments of science press deeper each year, tracing faint signals in cosmic light, in trembling space-time, in fleeting particles. Yet no matter how far they reach, one truth lingers. The field remains hidden, silent, invisible. What it is, or whether it can ever be fully known, remains an open question. But its implications are vast, stretching beyond the laboratory, beyond mathematics, into the heart of philosophy and the human spirit. A universe of futures. If the wave function is real, then the universe is not a line but a tapestry, every possible future existing side by side, woven into the hidden field. What appears to us as a single unfolding history may only be the path traced by one thread among countless others. Every choice, every accident, every fluctuation of a particle could create a divergence. Futures where stars live longer, where galaxies never form, where Earth spins barren beneath a different sky. Futures where history bends in directions never imagined. This vision raises unsettling questions. Do we live a singular destiny, or merely one of many? If every possibility exists, does choice have meaning, or are we only witnesses of one path through an infinite library? Free will, in a field of possibilities, philosophy has long struggled with free will, the tension between choice and determinism. The field intensifies that struggle. If the future is encoded in probability fields, then perhaps choice is an illusion, each outcome already inscribed in the hidden layers of reality. Yet, if collapse is genuine, if one path is chosen from the field, then perhaps choice is the very mechanism by which futures are selected. Consciousness itself may be the act of choosing, of collapsing possibility into the present. In this light, human freedom may not be erased by the field, but defined by it. We may be both limited and empowered, unable to escape the library of possible outcomes, yet able to trace one thread with awareness and meaning, the fragility of existence. Possibility of a false vacuum casts a shadow across reflection. If the universe rests on a metastable field, then existence is not eternal. It is fragile, balanced precariously on invisible scaffolding, and yet fragility gives weight to life. A universe that could collapse into silence at any moment makes every heartbeat, every thought, every fleeting connection infinitely precious. To exist in a fragile cosmos is to live on borrowed time, to recognize the miracle of each instant drawn from the field of possibility. The mirror of human meaning, the search for the hidden field, is not merely scientific, it is existential. Humanity has always sought foundations, gods, laws, certainties. The field suggests there may be no foundation at all, only endless layers of possibility. But perhaps this is not despair. Perhaps the field is a mirror, reflecting back our own longing. We search the cosmos not only to understand the universe, but to understand ourselves. The hidden field, whether it holds every possible future or not, reveals that reality is not fixed, not rigid, but fluid, open, alive with potential, and in that recognition lies a kind of hope. For if the universe is possibility, then meaning is not imposed from outside, it is chosen, moment by moment, from among the infinite futures the field provides. The silence of the stars, look again at the night sky. Each star gleams not as a fixed point, but as a wave in a vast, invisible sea. The galaxies stretch across darkness like ripples frozen in time, and beneath them, beneath space and time themselves, lies the silent field, invisible yet real, the ocean in which all futures swim. What humanity sees is only one page, one thread, but the silence holds more. The unborn stars, the unchosen paths, the futures that will never come to pass yet exist in quiet potential. In the end, the search for the field is not about equations or experiments alone. It is about wonder, about the realization that the cosmos is not a finished story, but a book still being read, still being written, in ways we can scarcely imagine. The final reflection, perhaps, the field that holds every possible future, is the ultimate architecture of destiny. Perhaps it is only mathematics, a useful description of probability. Perhaps it is information itself, the code from which existence emerges. We do not yet know. We may never fully know. But the search continues, because to search is what it means to be human. And so the story closes as it began, with silence. Not the silence of emptiness, but the silence of possibility. A silence filled with every path, every life, every cosmos that could ever be. In that silence, humanity listens.